So maybe enough for now about AI history and AI applications and foundation. Let's talk a little bit now about our course logistics. So this course is an artificial intelligence course at the master's level, which means that you can expect some challenge in completing the course. So it's going to challenge you and you learn a lot from it. As of the prerequisites, you are required to have some knowledge of programming and an understanding of probability. Python is the programming choice language for this course. So whether it's 2 or 3, we will accommodate both versions. Assignments, there will be 2 kinds of assignments: quizzes or conceptual assignments that will test your understanding of the lectures. Here, please make sure you read the instructions and questions very carefully before you hit submit of your assignment. There will also be some project assignments or programming assignments. The course offers an excellent opportunity for students to dive in Python programming while solving AI problems and learning its applications. So regarding course materials, we recommend but do not require this book, which is the main reference in the field, Artificial Intelligence, A Modern Approach, from Stuart Russell and Peter Norvig. This is like the encyclopedia of AI and represents an excellent reference for whoever wants to learn about the history of AI, the techniques in AI and applications. I use it as the main reference for my lectures, and you could find in this in the book website iema.cs.berkeley.edu a large number of resources that you could also look into it as you follow the lectures in this course. We are going also to post a large number of reading materials and useful links as we go in the course for each of the topics that we cover. What you will learn in this course is an introduction to artificial intelligence, the history of AI, building intelligent agent in search, games, logic, and constraint satisfaction problems. Machine learning algorithms is also a topic in this course where we dive into several machine learning methodologies. Applications of AI to natural language processing, robotics, and vision will be at the end of this course. We will learn how to solve AI problems through programming in Python. Our course roadmap is as follows. We will start first with the notion of rational intelligent agents, followed by different kinds of agents, including search agents in an informed search and informed search, adversarial search or games, followed by machine learning algorithms. We tackle then constraint satisfaction problems, or CSPs, and logical agents through propositional logic and first-order logic. The second topic is about Markov decision processes and reinforcement learning, and we finish the course with a set of applications to natural language processing, vision, and robotics. Now let's take a tour over all of these topics. So first of all, rational intelligent agents. This course is about designing intelligent agents, where an agent perceives its environment and acts upon that environment to achieve some task. An agent could be seen as a function f that actually goes from the set of percepts, or whatever the agent is perceiving from its environment, to a set of actions a in which the agent acts in that environment. So this is a way to see agents as a function. We care specifically about rational agents. These are agents that do the right thing. We'll define what is doing the right thing in the next lecture. Do the right things. Rationality is relative to how to act to maximize a performance measure that actually tells us how the agent is doing. AI aims to design the best agents or the programs that achieve the best performance given the computational limitations. An important aspect of agent is to see it as a bunch of hardware and a bunch of software. So we care about the software part or the program agent part in this course. Our first agents will be search agents, in which we design search agents that work toward a goal. The agent considers the impact of its actions on future states, which means that the agent is thinking about what to do to achieve its goal. The agent's job is then to identify the actions or series of actions that we could call a path that lead to the goal. A path comes in different costs and depths. We'll see 2 kinds of search. Uninformed search use no domain knowledge and include techniques such as breadth-first search, depth-first search, uniform cost search, etc. The informed search use some heuristic or information or rule of thumbs about how to reach the goal faster. And this includes techniques such as greedy search, A star, etc. So we go through these different techniques and you get a chance to implement some of them. Example of search agents include the 8-queen problem, in which on the chessboard we want to place 8 queens so that no queens attacks another one either horizontally, vertically, or diagonally. This is a search problem. You're going to search for possible configuration that actually, such as no queens attacks another one. A typical example of search agent is what we call route finding. So given a set of cities in North America, for example, and we have a map of it, the map is represented by a graph in which the nodes represent the cities and the edges represent the possible roads. You have the distance between the two cities that is actually highlighted on the edge. So suppose we want to go from the city of Las Vegas to the city of Calgary. There are different ways to do it. So we're going to explore the possibilities. So the aim of the agent is to do some exploration. And possible exploration would be to go, for example, taking this path here, or go to this path here, or take this path, etc., etc. So the paths have different costs, and this cost is the sum of the number of kilometers on the edges. So the role of search agent here is to find you a solution to go from city of Las Vegas to Calgary, but also to find you the optimal solution. We'll see different ways of how we can perform this kind of search. So once this path is found, the agent can execute the path to reach destination. Another important part of AI is adversarial search or games. There have been several games that actually were solved in AI. We have seen chess, Go, and Jeopardy before. So another example is the checkers. Chinook, for example, which is a computer program, ended 40 years' reign of human world champion Marion Tinsley in 1994. Checkers is considered as solved. The computer, or Chinook, can actually beat any human on chess, assuming the human is also playing an optimal play. So adversarial search, other name is games. Adversarial means that there is an opponent who we can't control. So how about game versus search? Game is also a search problem, but the optimal solution is not a sequence of actions of paths that lead to the goal, but it's a strategy or policy that actually help us win the game. In other words, if the opponent is doing A, then we do B. If the opponent is doing C, then we do D. It can be maybe tempting to write this as rules or hard code that, but it is tedious and fragile. So the idea is to write search agent that can play games and against opponents. So the concept and method that you will learn in this part of the course include the minimax algorithm, alpha-beta pruning, and stochastic games. A section of this course is devoted to machine learning. This is the current trend of AI today. So I'm going to talk about some methodologies. We won't cover all the aspects of machine learning, but consider it as a baby machine learning part in this AI course. So according to Tom Mitchell, which is one of the eminent researchers in machine learning is about how to create computer programs that improve with experience. And this experience comes from observations or data. So you want to be able to teach the computer how to learn and how to actually improve with experience. And this is at the core of machine learning. We'll address different kinds of learning. First, the supervised learning is when you have a label. In other words, we have an input, a set of examples, or instances, or objects, or points. And these examples have labels. They are tagged with some label. For example, this fruit described by XYZ is a banana. So we have a set of examples that actually have some features and have some labels. So this is the tag or the label attached to each of the instances. And the label Y is actually part of a small set of values, which is discrete. So it could be banana, not banana. It could be -1 + 1 or 0, 1. So we talk here about binary classification. And the output we want to build is a function H that goes from the set of inputs or description of the instances to the set of outputs. For example, suppose we have data about customers in a bank and we have all the information about the customers, their age, their gender, their occupation, their salary, etc. And we have some label for each of the customers that says whether he was approved credit, yes or no, whether for emails, whether it's a spam or non-spam, and so on and so forth. So we have what we call positive examples and negative examples, or two classes. And the idea is to find this function H that help us map the inputs or the descriptions of the customers to their credit status. Okay, so we could represent that. Suppose we are talking about two features, feature 1 and feature 2. We could put the examples as positive or negative on this two-dimensional space. So positive examples are those who got credit. Negative examples are those who were denied credit. And the idea is to find this decision boundary that actually separates here the positive from the negative example. So this is typically a typical example in supervised learning. So remember this term, supervised learning. Why it is supervised? Because there is someone who tells us which is a positive example and which is a negative example. The concept and method that you will learn here include supervised learning, classification, k-nearest neighbors, perceptrons, neural networks, linear regression, boosting, to cite a few. The second kind of learning is called unsupervised. And by unsupervised learning means that we don't have the label. So without label, we have examples without label. We have, for example, the populations or the customers, but we don't have any information about any kinds of label. No label is attached to them. So given these data points, can we find clusters of data points or of instances? So we are seeking to find a function f that maps the input x to a set of clusters. And this is actually completely unsupervised. We don't have any information about the label. We'll see different methods for unsupervised learning, and this include clustering with k-means and also association rules, among others. Our next topic will be constraint satisfaction problems, in which we talk about another kind of search problems. It's a search problems in which we don't care about the path to achieve the goal, but we care about the goal itself, such as solving a game. All paths are of the same depth, and the problem is generally formulated using variables instead of states. So we use variables, their domains, and some constraint that tells us how to solve the problem. Solving the CSP is then to find the assignment that satisfy all the constraints. We're going to learn concepts and methods, including problem formalization of CSPs, backtracking search, our consistency, and so on and so forth. A typical example in constraint satisfaction problems is Sudoku. So you all probably played the game Sudoku, in which you have a grid of 9 by 9 cells, and you want to actually fill the grid with numbers such that each 3 by 3 grid has digits between 1 and 9 with no repetitions. The lines have also all the digits between 1 and 9, and the columns have also digits between 1 and 9. Let's call these lines and these columns. Lines go between 1 and 9, and columns go between 1 and 9, right? So we could express that as a CSP by putting a variable by each of the cells. So each of the cells is a variable, XLC. This is X1, 2. And the constraints on these variables are that all 3 by 3 grid, row, or column must contain 1 to 9 digits, and all of them. The solution is then to find the assignment to the variables that satisfy all of these constraints. So we're filling the blanks. In other words, fill the blanks that actually were missing, such as all the digits in the line, columns, and 3 by 3 matrix are different. This is a typical CSP, and you will get a chance to play with these kinds of problems in your programming assignment. Our next topic is logical agent, in which logic can be used by an agent to model the word. Sentences in what we call propositional logic, invented by Boole a long time ago, and first-order logic have a fixed syntax. And we use symbols and connectives to model the word with logical expressions or sentences. For example, if it's hot and sunny, then we are going to the beach or the pool. So this is a logical expression using connectives such as the and, the or, and the implications, and also uses symbols such as pool, beach, sunny, and hot that represent different statements about the word. Syntax and semantic represent two important components and distinct aspects in logic. So the goal in using logic in artificial intelligence is to do inference. And inference is given a knowledge base, something you know about the environment, a set of sentences in logic, and given a query, for example, I wonder whether I should go to the beach or not, output whether the knowledge base entails alpha. So can we infer that we should do alpha based on what we know? And what we know is represented, as I said, in terms of sentences in logic. So in this topic, you will learn new concepts and methods, including modus ponens, which is an inference rule, sound and complete inference, horn clauses, etc. Reinforcement learning is our next topic, in which we design agents that evolve in a stochastic or uncertain environment. Agents learn from reinforcement or delayed reward. It's another kind of learning besides the supervised and unsupervised. Learning approaches for decision-making in situations where outcomes are stochastic involves an agent that continues to plan and learn to affect its environment. Reinforcement learning agents are driven by maximizing the reward on the long run, and we'll see those agents in the next topic of this course. Finally, we'll go through some applications of artificial intelligence to natural language processing, in which we are concerned with the interaction between computers and human languages, vision or perception that is concerned with image processing and building computers' vision agents, and the goal is information extraction from tasks such as manipulation, navigation, and object recognition. Finally, robotics that's concerned with intelligent agents that manipulate the physical world. Different aspects will be seen, such as planning of robot, motion, vision, and object recognition. I wanted also to have a historical moment today and dedicate this lecture to Alan Turing, who is a famous British mathematician and the code breaker of during the World War II. He proposed an operational test for intelligence that we have seen today, called the imitation game. He also proposed in his article in 1950, Computing Machinery and Intelligence, major components of AI, including language, reasoning, learning, and understanding. So I invite you really to go see this archive and check his article. It's a wonderful read. So let's summarize for today. We have said AI is a hard topic. It's hard because it involves different aspects, including computational complexity, languages, vision, etc. It's also a broad topic with high impact on humanity and society. What AI can do for us, and we have seen several applications, is just already amazing. AI systems, remember, do not have to model human or nature, but can act like or be inspired by human or nature. How humans think is actually beyond the scope of this course, and it's another branch of AI. And finally, the aspect rational agents, the agents that do the right thing, is the central approach or the central idea in this course. Note here, though, that the rationality is not always possible in complicated environment, but we still will aim to build rational agents. A recurrent question in the media and public opinion is whether AI is a threat to our humankind. Indeed, AI may raise some feeling of uncertainty about the future, and whether leaving people wonder whether they will keep their jobs, and whether AI systems will take over the world and exterminate the human race. This comes from different kinds of peoples at all levels in the society, including Professor Stephen Hawking, who told the BBC that the development of full artificial intelligence could spell the end of the human race. So he's in a good position to see how powerful are AI systems as he's using AI systems to communicate. In my opinion, AI is a flourishing and exciting field where everyone can contribute. We can contribute at the policy level, at the research level, computing level, privacy-preserving level, nature level, and so on and so forth. So we can be actors other than consumers of AI. And AI is a part of our lives anyway. So this is all what this course is about, giving you the principle and practice of artificial intelligence. I wish you all an excellent learning journey together. Thanks very much for being part of this course.